All righty. Up and running. 12 graphs, I think, something like that. So these tests today. And here are the graphing questions. So name that tune. Another name that tune. Sketching the following. Absolute value. E to the x. Quadratic. Logarithm. Another exponential. Natural log. Sinusoid. And let's push this chair out of the way, Renee. Let's see, we got a square root, point slope form, and then an estimation of the cosine of 6.27. All right, so let's have at it. Let's go back to the name that tune. None of these problems should take more than 10 seconds. They might take a little more than 10 seconds as I explain things as to how to do them. But if you've been doing the other lesson sets, just stream your way through the problems and you're all set. So I see 1800, it's a Y value, I'll take it. So far, I'm correct. Haven't made any mistakes. To get to 1920, I'll add 120. No mistakes yet. The logarithm. I know there's a 2 units of change from 5 to 7. Don't have to show this. 6 units to change, so I know I've got a 3-to-1 ratio every 4 units, I guess, from 7 to 11. Not sure of that, but let's just keep going. X equals 5, so x minus 5 gets us our domain restrictions. Numbers have to be bigger than 5. You don't see anything else over here. Throw in a 7, you got yourself a 2. Throw in an 11, 11 minus 5, 6 divided by 2 is base 3, so there is a 3-to-1 ratio. And I think that's good. So if you divide it by 3, right about here, you should have 2/3 of a change as a differential. And that just should take us to 1800 minus 120, 1680, I believe. So 5 2/3 should get us 1680. And we can start to fill up this entire curve with x's and y's that satisfy this equation. Let's look at 5 2/3. Minus 5 is 2/3, divided by 2 is 1/3. 3 to the what gets you 1/3. 3 to the what gets you 1/3. Hopefully you're seeing -1. So there you go, back 120, 1680. And you can keep doing that. So 2/9, 5 2/9, so on and so forth. There's the asymptotic behavior. Go to exponential log playlist. You get plenty of practice graphing logs. All right, no talking on this one, just gonna do what I see. I see y equals 7. I'm seeing 48. Next time I know it won't be 48. I'm seeing 7 to 31, which is 24. So I've got a cutting in half here. X minus 17 gets me my 0. Anything to the 0, 1. 48 and 7, 55. Drop in a 29. 29 minus 17 is 12. So every 12 units, I'm getting this differential of cutting in half. Okay. All righty. So we might as well nail one. So we said every 12 units, so 12 and 29 is 41. And if this was my second jump was 24, that's a jump of 12 on top of 7, should get me 19. Let's see how that works. 41 minus 10, 31 minus 7, 24. Divided by 12 is 2. This is a half squared becomes a 1/4. 1/4 of 48. Yes, we are definitely getting a pattern here. 28, 48, 24, 12. This gap is decreasing until we get to 0. So there's no differentials there, so we're hitting a height of 7, and I will call this function f of x, and therefore the limit as x goes to infinity, the bigger, the smaller, 6, 3, 1.5. This differential is heading to 0, so the function itself is heading towards 7. Okay? These numbers here are heading towards 7. Absolute value, V-shaped down. Remember, x minus 5 is a linear function that crosses through the x-axis at 5, 0. Slap an absolute value on this function and the negatives become positive. So this hinges at x equals 5. So at x equals 5, plug 5 in, you get -7. Therefore, the y-intercept is to the left of 5, that x value. This is an x value. Put a 0 in, we get -15, -7, -22. So the pieces are, I'm going up at 3 to 1 on the left. When I'm less than 5, I'm coming down at 3 to 1 when I'm greater than 5. 2 linear branches. All right, I see an exponential growth function. E is approximately 2.71. So I'm going to let myself do 4e to the 0 plus 3, and I'm going to do 4e to the 1. Now I like 1.1 plus 3. Those are my favorite. E to the 1.1, which is approximately 3. E to the 1.1, you go to a calculator, e to the 1.09. If you want to get an exact value for what makes a 3, then hit the button ln of 3, and you will get it. So that's an approximation. So what makes a 0? 2. E to the 0 is 1, so 4 plus 3 is 7. And my asymptote is 3. I can see my first jump from 3 to 7. I can see that jump. Don't have to write it eventually. And I'm going to triple that jump. I'm going to get 12 units. I'm going to triple it because I'm picking e to the 1.1, which means I'm picking 3.1. And if I 12 plus 3, I get 15. That was quick. 2x squared plus 8 minus 8x plus 5. So I'm going down, then up. Down is where my y-intercept is. We can prove it by doing minus b over 2a. Minus b, 8 divided by 4 is 2. Yes, 2. And yes, 0 is to the left of 2. It's on the down side. So I put a 2 in, minus 16, minus 8 plus 5, minus 3. And we can see the a term here. We can see that from -3 to 5 is 8 units. And from 2 to 0 squared is 4. And that's rise over run squared as measured from the vertex. And that's quite the pretty graph there. Yeah, a little rotator cuff problem. All right, logarithm. What do I see? I see an asymptote of x equals 3. I see a 1 to 5 ratio. 1 to 5 ratio. So my graph's going to look like that. I might as well get that one by making this the number 1. So the first thing I'm looking at is log base 5 of 0, which is undefined. Log base 5 of 1, which is the number 0. And I'm going to do log base 5 of 5, which is the number 1. Because what's in front of the logarithm? Multiplication. Multiplication. And I'm picking the easiest numbers to multiply by. Could have picked other numbers, but why work? So, what makes a 1? 4. That's going to get me 1 without even looking, because 0 times anything is 0, and I get that. The next one I'm going to get is 2 plus 1, which is 3. So that I don't even have to look eventually. All I have to do is make this equal 5. So that's 8. Okay, how far is it from 3 to 4? 1 unit. How far is it from 3 to 8? 5. And this is really divided by 1. So that division is really your first differential. I don't want to say that because if this gets more complicated, the argument, things could change. But in this model, well, that's quick and easy to do. All right, let's see if you're getting any better. I'm seeing an asymptote of -4. I'm seeing a first jump of 10. I'm seeing my next jump of 30. So let's put some numbers with it. Y equals -4. boom, boom. I'm gonna pick an 8. 8 is gonna get me 10 from 10 units of change. 10 minus 4 is 6. So that's 10 units of change. I'm gonna be 3 times that height, 3 times that differential over here, which is gonna be 30 units. 30 minus 4 is 26. And what makes 1? 7 times 1, 7 plus 8, 15. 15 is what makes a 1. So I'm doing 3 to the 0 and I'm doing 3 to the 1. And that's what I want my argument to equal. So there it is. We could put more points on there, knowing that 1 to 5 ratio, 1 to 3. What was it over there? 1 to 3, 3 to 1 ratio. All right, so the ln function, normally it's x equals 0. Normally it's the ln of 1, get you 0. Normally it's the ln of 3, which gets us 1.1. Now I'm going to change those numbers. X minus 1, it's not 0 anymore. It's 1. I want a 1. I'm going to pick a 2. I want the number 3. I'm going to pick a 4. Now, I'm multiplying things by 4. Okay, so therefore, when I put a 2 in, this multiplication disappears. I don't get 0 anymore. I get 7. I get that number. And when I make this 3, I get 1.1. And 1.1 times 4 is 4.4 plus a 7 is 11.4. That number just changed. And I want the number 3. So, yeah, I already talked about that. 4 minus 1. I guess that's my graph. Yeah, let's put a number in here. Let's see how it works. 2 minus 1, 1. What's the ln of 1? Well, I know either 0 is 1. So the ln of 1 is 0 times 4. 0 plus 7. Oh, yeah. Yeah, and sure looks like if I put 3 in here, right? Of course, I want 3. So it's, remember, it was x minus 1. So I need 4 in order to create this. And this is 1.1 times 4 plus 7. I think I can do that in my head. The sine function. The sine function starts over here at 0, goes up to a height of 1. That's a height of 1. That's the mid-range, and that's a 0. And it goes down to -1. Okay, so what do I have? I have the first 90 degrees of triangles. There's a triangle, there's the height, the sine function, the height. Heights are getting bigger. Heights are getting bigger till I max out at 1. And then they start to come down again. Those heights come down again, back to the midline, and then those heights get to be negative until they get to -1, and then they come back again. So there's one period of the sine function. Let me erase some things here. I don't have a single, yes, I have an eraser. All right, so how is this period going to change? We've got the shape of the sine curve. We know it goes from 0 up to 1, down to -1. I think I'm going to last with this marker. That's +1 to -1. Goes through the origin at a 1-to-1 rate, by the way. We'll talk about that as the term goes on. And 1 revolution, or 6.28. Let's go with some decimal numbers here. Roughly 6.28 radius lengths later, I'm back where I started from. 0. But my midline isn't 0 anymore, it's 17. And I'm not going up and down 1 anymore, because I'm multiplying 5 times the calculation that gets me plus and minus 1. That's really what I've got. I've got the sine of x over 4 only kicks out numbers 1 to -1, but I'm multiplying them by 5. So I think from 17, if I'm going up 5, I'm at 22. And if I'm going down 5, I'm at 12. So the range is from 22 to 12. Y values. Less than or equal, because that's a question. That's a test question. You got to learn that. So I'm asking it. All right. So now what happens? I've got to make the argument 0. Oh, that's easy. It's still 0. And I got to make x over 4 6.28. I think I got to multiply this by 4. Let's go back and change it to 2 pi. It's a whole lot easier to multiply 2 pi by 4. So why don't I call it 8 pi? Yeah, well, let's throw 8 pi in here. And let's divide it by 4. Yep, 1 revolution. Then you got all kinds of symmetry. 4 pi, 2 pi. I put 2 pi in here. 2 pi divided by 4 is pi over 2. Where's pi over 2? Top of the circle. What happens at the top of the circle? Your heights are a max. Okay, that's enough of a chat about that today. We'll talk about it some more tomorrow. I'm seeing what a lot of my students are confusing with logarithms, unfortunately. But if we keep talking about it, maybe that confusion will stop. Minus 2, because I want 3 times the square root of 0 minus 7. And I like 3 times the square root of 25 minus 7, just as 2 solutions. All right, because I know if I make this 28, nope, sorry, 23. If I make that 23, I get this calculation. And that gets me a y value of 15 minus 7, which is 8. Somewhere on here, if I pick 23 units, I'm getting 8 units out. I just satisfied an equation. And there's an infinite number of satisfactions, right? And the most important one is dropping in a -2, because square roots are distances and square roots can get smaller. Yeah, 1 times 1 is 1. Yep. They can get even smaller. A half times a half. Well, that's a fourth. They could even get smaller. A third times a third, a fourth times a fourth. In fact, they can go to 0. I can't draw it, but 0 times 0 is 0. So the square root of 0 is, I think, smallest square root I can get. What makes a 0? -2. That gives me this calculation, which gives me minus 7. Yeah. And how far is it from minus 7 to 8, you ask? 15 units. And how far is it from -22 to 23? 25 units. But what kind of units are we? What kind of change are we canceling out? Square root change. And 15 divided by 5 is 3. And that's one big coincidence for that multiplier. Boy, these coincidences in math, there's so many of them. Point slope. If you're getting on the other side of the test, problem 2 or 3, name 3 coordinates. I see a 2, I'm changing by 4. I'll do the x column, the y column. I'll start with a 4. 2, 4 gets me 0 equals 0, which is true. That satisfies that equation. And I think I'm going down 3. And I think I know how to plot those points. Let's call that 1. I'll estimate 2, 4. I'll estimate 6, 1. I can even do 10, -2. But I'm running out of room, so why don't we just take A and B, let's call that coordinate A, coordinate B, plot them, and recognize that a one-dimensional shape is a line. Cosine is 6.27. Well, in the last problem, we looked at heights. Cosine's widths. Widths in the unit circle get biggest over here at 0, and once around the circle. Oh yeah, we called that 6.28 2 minutes ago. And I'm at 6.27. Well, you tell me how I'm going to draw that. I just said very quickly 0.999. I said, God, it's almost 1. Right? And Google came back with another 9. And then a number after it. But there were 4 9s before it went down at all from the 9s. Anything near 1, and I'm giving you credit. I don't care if you say 0.983. I'll still give you credit. You're in the right ballpark. Got to start somewhere. It's good if you're playing a game to be in the right ballpark. Yep, getting silly. All right, stay safe, stay warm. We have nice warm weather coming, but then it's going to turn cold again. Oh well.